Good morning, students. Now let us see about the refraction of light. Now light seems to travel along a straight line path in transparent medium. Now what happens when the light enters from one transparent medium to another? For example, when the light enters from a glass slab, or when the light enters from the air to the into the swimming pool where water is there. So in that case here we have to find out whether it still moves along a straight line or changes path or direction. So for that here we have to learn about the refraction of light. So this process, refraction of light, it helps you to understand the path of light along when it moves from one medium to another. Now you must have observed that at the bottom of the tank or a pond containing water, it appears to be raised. Means we feel that it is not that deep. Now similarly, when the thick glass slab is placed over some printed matter, the letter appears to be raised when viewed through the glass slab. So why does this happen? Now also, if you take a pencil which is partially immersed into the water in a glass tumbler, it seems to be displaced. It doesn't look straight. We feel that part of the pencil, it gets displaced from the water, or it is not a straight line. So this shows you that, or this that the lemon kept in the water in a glass tumbler, it appears to be bigger than its actual size when viewed from the sides. So all these experiences of our day-to-day life, it shows you that there is apparent displacement of the pencil, or there is apparent this one a size of the lemon which appears to be bigger. Apparent means it is not the actual. It looks as if the lemon is bigger, but it does not become big. The image looks bigger. Then the depth of the pond or a swimming pool, it does not reduce. Its apparent depth becomes less. Means the depth appears to be less. So does the pencil appears to be displaced to the same extent if instead of water, if we use liquids of kerosene or turpentine? So will the letters appears to be raised if instead of this one glass slab, if you replace it with some plastic slab? So all these things we can understand with the help of refraction of light. So light travel in the same direction in all media. So it appears that when traveling obliquely from one medium to another, the direction of propagation of the light changes. And this change in this phenomena of changing the direction or the propagation of the light when it travels from one medium to another is called as the refraction of light. Now let us understand this here with the help of this refraction through a rectangular glass slab. Now this refraction through a rectangular glass slab, this you can have then experiment. This you must be having this in the practicals also. Now what you do here, take a sheet of paper, and that sheet of paper, fix a sheet of white paper on a drawing board using drawing pins, and place a rectangular glass slab, like this is the rectangular glass slab, over this paper. Now draw the outline of the slab with the help of pencil and name this outline as A, B, C, D. Now at this point O, here draw the perpendicular, and then along this perpendicular here, O, N dash, here draw a line. Let that be called as the incident ray, and let it be at an angle of 30 degree. So this angle of incidence, we denote it as I. Angle of incidence is the angle made by the incident ray with the normal. Now this angle of incidence I here, this is there. Then on over this incident ray, fix 2 points, pins E and F. After that here, what you do, now through this other side of the slab, you try to watch see the images of these 2 pins placed at E and F, and accordingly place 2 pins G and H on this side CD of the glass slab. After that, remove the glass slab, and then here also you draw the perpendicular. Now this join this O and O dash points. Now this O and O dash points, when you join here, now this ray O dash, this is the refracted ray here, and then this ray of light emerges from this point O dash through the from the glass slab. So this GH, this is the this is the reflected ray. So what we observe, this is the emergent ray, sorry, the GH is the emergent ray. So which rays are there? EF is the incident ray, then O dash, O dash is the refracted ray, and then GH is the emergent ray. Now this angle here, this one at this one, angle of incidence is I, angle of reflection here at this point is R1, and here this angle of emergence, it is R2. After that, here what you do here, this one, now view this refraction, this is due to the this. So here we find out that the following are the laws of refraction of this light, that the incident ray, the refracted ray, and normal to the interface of two transparent media at the point of incidence all lie in the same plane. Now the ratio of the sine of angle of incidence to the sine of angle of refraction is constant. So for the light of a given color and for the given ray pair of media. So this is known as Snell's law of refraction. So if the angle of incidence is I and R is the angle of refraction, then we get sine I upon sine R. This is equal to some constant, and that constant value, it is called as the refractive index of the second medium with respect to first. So in this experiment, the first medium is air and the second medium is glass. So the refractive index of the glass, it will be given by the formula sine I upon sine R. So here in the figure, what we see, this here, this one, see, this is the I1 is the angle of incidence, and then this here, this R2, this is the angle of refraction. So sine I upon sine R, this is equal to the refractive index, and that is that gives you the refractive index. Now next we will see what do you mean by the refractive index. Now you have already studied that the ray of light that travels obliquely from one transparent medium into another will change its direction in the second medium. Now the extent of change in direction that takes place in a given pair of media is expressed in terms of refractive index, the constant appearing on the right hand side of the equation, this one, in equation 10.4. Now refractive index, it can be linked to the important physical quantity, that is the relative speed of the propagation of the light in different media. It turns out that the light propagates with different speed with different media. Light travels a maximum in the vacuum with the highest speed of 3 into 10 raised to power of 8 meter per second. In air, it is slightly marginally less, and considerably it reduces in glass or in water. Now the value of the refractive index for a given pair of media, it depends on the speed of the light in two media. Now consider the ray of light traveling from medium 1 into medium 2 as shown in the above figure. Let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. Therefore the refractive index of medium 2 with respect to the medium 1 is given by the ratio of the light in medium 1 and the speed of the light in the medium 2. This is usually represented by the symbol refractive index of the second medium with respect to the first. It is given by second medium. N21 means refractive index of the second medium with respect to the first. It is given by speed of light in medium 1 upon speed of light in medium 2. So by the same argument, the refractive index of the medium 1 with respect to the medium 2, it is represented as N12. So here in which order this 1 2 is written and this how to read it, that you understand. One N21 is what? Refractive index of second medium with respect to the first, and N12 is refractive index of first medium with respect to the second. So the refractive index of first medium with respect to the second, it will be given by the reciprocal of the above formula. So it will be given how speed of the light in medium 2 upon speed of the light in medium 1, that is equal to V2 upon V1. So if the medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to the vacuum. So this is called as the absolute refractive index of the medium. So it is simply represented as N2. Okay, if c is the speed of the light in air, and v is the speed of the light in the medium, then the refractive index of the medium is given by a speed of the light in air upon speed of the light in the medium. Means here, for if the glass is there, then how you will write down refractive index of glass will be given by speed of the light in air upon speed of the light in glass, that is c upon v. And what value of c you will take it? 3 into 10 raised to power of 8 meter per second. Now absolute refractive index of the medium is simply called its refractive index. Now refractive index of the several media is given in the table, and it is different for the different medium. So the first column, it gives you the material medium, and the second column, it gives you the refractive index. So the refractive index of the air, you can see, is 1.0003. it is approximately taken as 1. Ice, it is 1.31, water 1.33, alcohol 1.36. So this way the refractive index, you can see, as you move down the table, it goes on increasing. For crown glass, it is 1.52, Canada balsam glass, it is 1.53, rock salt, it is 1.54, and then slowly when you come to the diamond, it has got the highest refractive index, that is 2.42. Now kerosene, we know. Now one more relationship is there between the the kerosene, it is lighter than water, so it floats on water, but the optical density of kerosene, it is more than that of water, because refractive index of water is 1.33 and refractive index of kerosene is how much? 1.44. it is more. So optically kerosene is denser than that of water, though the mass density of kerosene is less than that of water, because kerosene, when mixed with water, it floats on water. Now next we will see here this one, refraction by the spherical lenses. Now spherical lenses means, here see, you must have seen the people using the spectacles. Now these spectacles, they are made up of lenses, and those lenses, they are the spherical lenses. Also in the microscope, or you must have seen the lenses are there. So those lenses are also the spherical lenses. Now this spectacles, if you touch with your hand, you can see that the surface is not plain, it's the curved surface. So it is thicker in the middle and thinner at the edges, or sometimes it is thinner at the middle and it becomes and it is thicker at the edges. So there, now we shall discuss this spherical lenses in this chapter. Now there are two types of lenses we have to learn here: convex lens and the concave lens. Now the transparent material bound by two surfaces of which one or both surface is spherical forms a lens. This means that the lens is bound by and at least one spherical surface. In such lenses, the other surface would be plane. Now the lens which have two spherical surfaces bulging outward, such a lens is called as the double convex lens, or it is simply called as the convex lens. Now here see, here we have to learning only double convex lens and double concave lens. Now this figure, if you see what we see, now these two surfaces, both the surfaces, they are convex. So, and this lens is called as the double convex lens or simply a convex lens. Whereas here these two surfaces both are concave. So this lens, it is called as the this concave lens. Now this is the convex lens and this is called as the converging lens also. And this lens here, the rays of light, they diverge after passing through it. So this lens, concave lens, this is also called as the diverging lens. Now here we have to understand the terms which are there in this lenses. Now the center of curvature of the lens, it is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2. Now here see, you can see this figure here carefully. Now this lens, this is a double convex lens or simply a convex lens you can take. Now O is called as the pole of the lens. Now F1 is the focal length of the lens. Now this lens, these are the two surfaces, they are the part of two spheres. So naturally it will have two principal focus and two center of curvature. Rest all terms, they are just as we have learnt in the mirror, in the spherical mirrors. So F1 is the first focus, principal focus. F2 is the principal focus which lies on this side. Then C1 and C2, these are the two center of curvatures of these lenses. Now also we know that OF1 is the focal length of the lens. OF2 is also the focal length of the lens. Now this distance OF1 or distance OC1, this is the radius of curvature. So that is double the length of the focal length. So this C1, it is also denoted as 2F1 and this C2, it is represented as 2F2. Now same way for this concave lens also, it will have the pole of the lens or the center of the lens, and then it will have the principal focus F1 and the center of curvature 2F1. Again we get that this 0F1, this is the focal length, this is half the radius of curvature 0F1. Now such lenses here, now imaginary straight line which is passing through the two centers of curvature, this is called as the principal axis. Now center point of the lens is the optical center and it is usually represented as O. Now the ray of light passing through the optical center of the lens passes through without suffering any deviation. The effective diameter of the circular outline of the spherical lens is called as the aperture. Now next we will see here this one. This image formation by the lenses. Now the image formation by the lenses, this also is very easy. It is just like we have learnt the mirror formation, this image formation in case of spherical mirrors. Now for drawing the ray diagrams in lenses of the spherical mirrors, we consider any two of the following rays. Now the ray of light from the object parallel to the principal axis after refraction from the convex lens passes through the principal focus on the other side of the mirror as shown in the case A. Now in concave lens, the ray of light here parallel to the principal axis, it diverges when passing through the concave lens, and then when you extend it, it appears to come from the principal focus on the same side. Clear? Now the second ray of light that we have to study is this one. Now the ray of light which is passing through the principal focus, after passing through the lens, it becomes parallel to the principal axis on the other side. And for the concave lens, how it is, the ray of light which appears to pass through the principal focus after passing through the concave lens becomes parallel to the principal axis. Now third one, the ray of light which is passing through the optical center of the lens will emerge without deviation. So this is illustrated in the figure 10.15. Now the ray diagrams for the image formation of the convex lens for a few positions of the object is shown in the figure 10.16. Now the ray diagrams representing the image formation in a concave lens of the various figures is shown. Now here, if this is the case A, when the object is at infinity, like the sun image, then the image will form at the principal focus on the other side. Now if the object is beyond the center of curvature, then the image will also be formed. Image will be formed between the principal focus and the center of curvature on the other side. Now if the object is between the center of curvature and the principal focus on one side, then the image will be formed if the object is at the center of curvature on one side, then the image will also be formed at the center of curvature on the other side. Now in this case here, the object is between the center of curvature and the principal focus, then the image is formed beyond the center of curvature. So you can see again from this table here, this one, this table you observe, so you will see that when the object is at infinity, image is formed at focus f2. Image is relative size of the image is what? Highly diminished point size. It is real and inverted. When the object is at focus f1, then the image is formed at the infinity. Relative size of the image, it is infinitely large or highly enlarged. Then again the image is real and inverted. If the object is beyond the center of curvature, that is 2f1, the image is formed between f2 and 2f1. Between f2 and 2f2, again it is real and inverted. Now consider this case. Now if it is at between f1 and 2f1, image is formed beyond 2f1. So the second and the fourth one, they are just the vice versa of each other. Okay, now if the object is at 2f2, then the image is formed at 2f2, and size of the image is same as that of the object. Nature of the image is real and inverted. Real means the image can be obtained on a screen, and inverted means upside down. If the object is at focus, now the first and the fifth one, they are the converse of each other. At f1, image is formed at infinity. Size of the image is relatively large or highly enlarged, and real and inverted. Now if it is between focus and the optical center, then the image is formed on the same side of the lens as that of the object, and this image is enlarged, and it is virtual, means it cannot be obtained on a screen, and it is the erect image. Now the image is formed by the concave mirror, concave lens. It is of only at two positions. Now if the object is at infinity, image is formed at focus f1. It is highly diminished point size, virtual and erect. And if it is between the infinity and the optical center of the lens, it is formed between f1 and the optical center. It is diminished, virtual and erect. So the image formed by the concave lenses, they are always virtual and erect. So you can understand this with the help of this one. If the object is at infinity, image is formed at the principal focus. If the object is between 2f1 and f1, then the image is also formed. Object is between the pole of the optical center and f1, then the image is also formed on the same side, and it is enlarged image. Now sign conventions for the spherical lenses. Now we know that for lenses we follow the sign convention similar to the one used for the spherical mirrors. We apply the rules of signs of distances, except that all measurements are taken from optical center of the lens. According to the convention, the focal length of the convex lens is positive and that of the concave lens is negative. You must take care to apply the focal length is of convex lens is positive and that of the concave lens is negative. Now lens formula and the magnification. As we know that the formula for the spherical mirrors, we also have the formula for the spherical lenses. Now this formula gives the relationship between the object distance u, image distance v, and the focal length f. Now the lens formula, it is expressed as 1 upon v minus 1 upon u. This is equal to 1 upon f. Now the lens formula given above is general and is valid in all situations for any spherical lenses. Now take proper care of the signs of different quantities while putting numerical values for solving problems relating to lenses. Now we know that magnification. Now magnification means what? It is produced by the lens similar to that of the spherical mirrors, is defined as the ratio of the height of the image to the height of the object. It is represented by the letter m. If h is the height of the object and h dash is the height of the image given by the lens, then the magnification produced by the lenses is given by m is equal to height of the image h dash upon height of the object h. Now magnification produced by the lens is also related to the object distance and the image distance. The relationship it is given by magnification m is equal to h dash upon h or is equal to v upon u. Now next we will see about this one, power of the lens. Now ability of the lens to converge or diverge light rays depends on its focal length. Now the convex lens of short focal length, it bends the light rays through the large angles by focusing them closer to the optical center. Similarly, the concave lens of very large focal length causes higher divergence than the one with the longer focal length. Now, degree of convergence or divergence of the light rays achieved by the lens is expressed in terms of the power. Now, the power of the lens, it is defined as the reciprocal of the focal length. It is represented by the letter P, and P is given by 1 upon F. Now, the SI unit or the power of the lens is diopter, and it is denoted by D. If F is expressed in meters, then power is expressed in diameters, is in diopters. Thus, 1 diopter is the power of the lens whose focal length is equal to 1 meter. Means if the focal length is given in centimeter, that you have to convert it into meter first and then take the reciprocal. So that will be the power of the lens in diopter. Now the power of the convex lens will be positive because focal length is positive, and power of the concave lens is negative because the focal length is negative. Now opticians prescribe corrective lenses indicating their powers. Let us say the lens prescribed has power equal to 2 diopters. This means that the lens prescribed is convex. Focal length of the lens is plus 0.5 meter. Similarly, the lens of the power minus 2.5 diopter has a focal length of minus 0.40 meters. Now, many optical instruments consist of the number of lenses. Now, these are combined to increase the magnification and the sharpness of the image. Now, the net power of the lenses placed in contact given by the algebraic sum of the individual powers P1, P2, P3, so on. So, P is equal to P1 plus P2 plus P3 and so on. Now, use of the powers instead of focal lengths for lenses is quite convenient for the opticians. Now, during eye testing, the opticians put several different combinations of the corrective lenses for the power, and the optician calculates the power of the lens required by simple algebraic addition. For example, the combination of the two lenses of the power plus 2 diopter and 0.25 diopter is equivalent to a single lens of power 2.25 diopter. Now, simple addition property of the power of lenses can be used to design the lens system. So, I think now with this chapter is complete and the refraction of the light is also over.